So this video goes over section 5.6 on molar mass and mass to mole conversions. So the molar mass, as the name says it, it's the mass of 1 mole. Molar refers to mole. So it's the mass of 1 mole of any substance, and it's reported in grams per mole. So the unit is always gram per mole, gram/mole. And so these molar masses are given in the periodic table. And if you look at the periodic table below the symbol and the name, you see the atomic mass, the number with decimal. And so this atomic mass, for example, if you look at carbon, it says 12.01. And up to now, we've learned that it was the mass of 1 atom of carbon. And it's 12.01 atomic mass unit. AMU is atomic mass unit. Well, now we will use those same numbers, but we will call them our molar masses. And the unit now will be grams per mole. So it's the same numbers if you talk about 1 atom or a mole. What changes is the unit, right? So what it means is that 1 mole of carbon atoms weighs 12.01 gram. So earlier you remember how we had a mole of carbon atoms in a balance, and you didn't pay attention maybe to the mass that was written on the screen, but here the mass displayed by the balance is 12.00 grams. And so when we have 1 mole of carbon atoms, we have 12 grams of carbon. So we will learn to calculate how to calculate molar masses for a compound, because the molar masses on the periodic tables are just for the element. So to calculate the molar masses of compounds, you will add the molar masses of the elements, but by taking into account the number of atoms of that element in the formula of the compound. So you want to gather all the molar masses of each element, in the formula, multiply the molar masses by the subscript for that element, and calculate the molar mass of the compound by adding the molar masses of each element. So the best is to go through an example to see how we do this. And we will calculate the molar mass of CO2, carbon dioxide, as an example. Notice how it is also sometimes called molecular weight, because that CO2 is a molecule, and so you can also call it a molecular weight. I prefer molar masses, and I will always use molar mass. So in CO2, the formula of this compound, we have 1 carbon and 2 oxygen atoms, right? So this formula tells us that the 2 here, the subscript, belongs to oxygen. The 1 for carbon is implied. And so you will gather the molar masses of carbon and of oxygen, because that's the 2 elements you have in this formula. And carbon, of course, you will need to have a periodic table available when you do this, always. And so molar mass of carbon is 12.01 grams per mole. And the molar mass of oxygen is 16.00 grams per mole. So notice how capital M here symbolizes molar mass. It is not a unit. Do not use this as a unit. It's only standing for the words molar mass. I want you to always write that your numbers are in units of grams per mole. Okay, that's the unit of the molar mass. So we will multiply the molar mass of oxygen by 2, because we have 2 oxygens per formula. And we will add that to the molar mass of carbon. And when you take the sum of all of this, it's 44.01 gram per mole of CO2. Notice here that we are doing an addition when we are adding the molar masses, and so we need to keep the same number of decimal places as, you know, the least number we have. The periodic table I provide has most of the time has 2 decimal places, so most of the time and almost all the time I will expect 2 decimal places for your molar masses. You should not drop those decimals. So let's practice by calculating the molar mass of lithium carbonate, Li2CO3, which is used to treat bipolar disorder. So we have this formula, Li2CO3. So you will want to gather the molar masses of Li, which is lithium, and carbon, and oxygen. So from the periodic table, we know that 1 mole of lithium is 6.94 grams per mole. And we already know about the mole of carbon, 12.01 grams per mole, and 1 mole of oxygen is 16.00 grams per mole. Next, you will multiply the molar mass by the subscript if it's different than 1. So we will need to take 2 times the molar mass of lithium and 1 time the molar mass of carbon and 3 times the molar mass of oxygen. So you calculate those intermediate answers. And here, because the 1, the 2, and the 3 are exact numbers, so you keep well, you keep yeah, the same number of sig figs, but for when you calculate molar masses, as I said, I always want you to keep 2 decimals, right? And so when you're adding, all your values should have 2 decimals. So the molar mass of the compound should also have 2 decimals. And so here, when you add them together, the molar mass of lithium carbonate is 73.89. So make sure you know how to do this. And let's practice some more with another compound formula. So please pause the video and learn how to do this on your own and before you watch the answer. It is important you learn to do this on your own. So here, Al2SO4 3 times. So it's aluminum, and the SO4 is the sulfate polyatomic ion. And there are 3 of them. So it is important to pay attention to the number of atoms you have per formula. So here you have 2 aluminums, and you have to be careful. You have 3 sulfates, and each sulfate has 1 sulfur and 4 oxygens. So the number of sulfur is 3 sulfate times 1 sulfur per sulfate, and so that's 1 times 3 sulfur. And for oxygen, it's 4 times 3. You multiply the 2 subscripts because it's 3 sulfates times 4 oxygens per sulfate. So that means you will multiply 16 grams of moles per oxygen times 12. The sulfur, you will multiply 32.07 grams of moles per moles of sulfur times 3. And the molar mass of aluminum is 26.98 times 2. So make sure you have the correct numbers. You calculate those intermediate answers and you add them all together. And the molar mass of Al2SO4 3 times should be 342.17 grams per mole. Again, keep 2 decimal places. Alright. So make sure you know how to do this properly. And so the molar mass relates the number of moles to the number of grams of a substance, right? And so therefore molar mass can be used as a conversion factor. because it relates grams to moles, and this can be written as an equality. And for example, the molar mass of H2O is 18.02 grams per mole. And so written as an equality, it's written as 1 mole of H2O is equal to 18.02 grams of H2O. You really should see the molar mass like this and write it like that actually on your papers. Because this shows you that you can use it as a conversion factor, because, you know, back from chapter 1, we learned that from an equality, we can write 2 conversion factors. And so this equality can be written as 1 mole of H2O over 18.02 grams of water, or the grams of water over 1 mole of water. Right, and you will choose the correct conversion factor depending on the given amount you start with. So let's practice calculating moles or grams of a substance from the grams or the moles. So this procedure shows you how first you want to gather the information from the text. So state the given and needed quantities. Step 2, you want to write a plan to convert the moles to grams or grams to moles, depending on what you have as a given. In third step is to determine the molar mass and write the conversion factors. And step 4 is set up the problem to convert moles to grams or grams to moles. So let's go through this process by following an example. Calculate the moles of carbon in 0.0265 grams of pencil lead. So pencil lead is what you are using when you are writing with a pencil, right? Inside the wood, it's or the plastic now. You have carbon is the pencil lead. It's carbon graphite. So if you look at this text, the given here is 0.0265 grams of pencil lead, knowing that pencil lead is made of carbon graphite, and so you can write its grams of carbon. What we need, so what is the question asking for? It's asking for a number of moles of carbon contained in that small amount of pencil lead. So you see here that the roadmap will show that you start with grams and you want moles, right? So if you need help with that, it's nice to write a roadmap that shows your starting unit and the final unit. And here we know we have a relationship, a direct relationship between grams and moles, and that's the molar mass. That's what the molar mass is all about. And so you want the molar mass of carbon. So you look at your periodic table. So notice here how you will not be given the molar masses. You will have to automatically reach for your periodic table and find them in there, right? You have to have that reflex of going to your periodic table when you need the molar mass. And so for carbon, it's 1 mole of carbon is 12.01 grams of carbon. So it's written as an equality here because it's easier to see from this equality that you can write 2 conversion factors. And because we start with grams of carbon, the given will be in grams of carbon. So the conversion factor will have to cancel the grams of carbon. So the grams of carbon will have to be in the denominator of your conversion factor. And so you will write it like this with 1 mole of carbon on top and the 12.01 grams on the bottom. And so when you put this all together, always start your calculation with the given amount. So 0.06265 grams of carbon, it's in the numerator. So you could draw a line below and a 1 under in the denominator to remind you that this is in the numerator. times the conversion factor, such that you can cancel grams. So the grams of carbon are on the bottom and the 1 mole on top. You can see that the grams of carbon cancel, and you're left with moles. So that confirms it's the way you want to set up your calculation. Next, you type in your calculator 0.0265 divided by 12.01, right? 12.01 is in the denominator, so you divide. And if your calculator is in decimal display, it will show 0.002206. And if you are in scientific notation display, and you can always change that by doing the second function, DRG, you know, the degree key, because the degree key has the SCI/engineering above. So the second function of the degree key is to change the display mode to floating point, scientific notation, or engineering. So always use floating point or scientific only. So in scientific notation, it's 2.20649, etc. times 10 to the negative 3. So you want to round this properly, and in the given amount, we have 3 sig figs because the 2 zeros are not significant, and the 2, 6, and 5 are the significant figures. The 1 mole is exact, it's 1 mole exactly, and the 12.01 is has 4 sig figs. So the least number is the given amount with 3 sig figs. So you want to keep 3 sig figs, and so you keep the 2.2, and what comes after is a 0. And you keep that number, but what comes after the 0 is a 6, which means you will need to round up. So your 0 becomes a 1 times 10 to the negative 3 moles of carbon. It would be fine here to give the answer in floating point, and it would be 0.00221 moles of carbon. So let's go through some learning checks. Silver metal is used in the manufacture of tableware, mirrors, dental alloys, and jewelry. And so if the design for a piece of jewelry requires 0.750 moles of silver, how many grams of silver are needed? So let's say you're helping the manufacturer of a jewelry, and you've designed a piece requiring a number of moles, and you want to know, in practice, how many grams is that? So out of this text, the given amount is 0.750 moles of silver. Ag is the symbol for silver. The question is asking for how many grams of silver. So that's what we need to find. And so here, if you write the roadmap, you will see that we start with moles of silver, and we want to finish with grams of silver. And fortunately, it's just a direct relationship between moles and grams, and if you use the molar mass of silver. So you need to gather the molar mass of silver from your periodic table. And so it's 1 mole of silver is 107.9 grams. So the periodic table I give is actually 107.87. This slide shows 0.9, but you can do it with 0.87, and you should see that it should be very close to this, it should be the same answer. So out of this equality coming from the molar mass, we have 2 conversion factors. So which one we will be using? So for this, you need to look at the given amount, The given amount is in moles. So you will want to use the conversion factor that has the moles on the bottom, and so that you can cancel moles of silver. So we will use the first conversion factor here, right? The one that has the mole of silver on the bottom. So when we write the full calculation, you always start with the given amount. So here it's 0.750 moles of silver. This is in the numerator. Then you multiply by the conversion factor, and the conversion factor we said should have the moles on the bottom so that moles cancel, and 107.9 grams of silver will be on top. So you do this on your calculator, 0.750 times 107.9 or 0.87, it's fine. And you get 80.9025. That's the calculator answer. So you need to round properly. So if we look at the given amount here, there is 3 sig figs because the 0 after the 5 is significant. It is significant because we see the decimal point. Okay, so 750 here are significant. The molar mass has 4 sig figs and the 1 mole is exact. So the limiting number of sig figs is 3. So we need to round to 3. So we will keep the 8, the 0.9. What comes after the 9 is a 0, so you round down and you keep it like this, 80.9 grams of silver. Another practice problem, this time with salt. You probably have something like that at home. A box of salt contains 737 grams of sodium chloride, NaCl. How many moles of NaCl are present in the box? So from the text, you want to extract the given amount. And so please pause the video to work this on your own before you watch the answer. So again, from the text, you can extract the given amount. And here it's 737 grams of sodium chloride. What we need, so what is the question asking? How many moles of NaCl are present in the box? So we are trying to find the number of moles of NaCl that 737 grams of NaCl contain. So you want to write the roadmap that shows how what you start with and what you want to end with. And so here it's grams of NaCl that are given and moles of NaCl that are wanted. Again, when you have grams versus moles, you should always think molar mass. Molar mass is what relates grams to moles. And here it's going to be the molar mass of NaCl. You need to adapt the molar mass to the substance in question. So take your periodic table, gather the molar mass of Na and the molar mass of Cl. And so add it together. So molar mass of Na is 22.99 and chlorine is 35.45. When you add them together, the mole of one NaCl is, so 1 mole of NaCl has a mass of 58.44 grams of NaCl. So write it as an equality like this. This really shows you the two parts of the conversion factor. There are 2 conversion factors out of this equality. And so which one we will use here? Is it the first or the second? And so to decide that, you need to look at the given amount and you see that it's grams of NaCl. So you will want the conversion factor to cancel grams of NaCl. So here you will want to use the second conversion factor such that the grams of NaCl will be cancelled because they are on the denominator. And so when you write your complete calculation, always start with the given amount. 737 grams of NaCl, and please write the full units, grams of NaCl. You will see later on how this is important to write the full unit, not just grams and moles, because here we are dealing with only one substance, but later on we will deal with more than one in one calculation. So you want to identify, grams of what and moles of what. So 737 grams of NaCl times the conversion factor that has the grams on the bottom and the mole on top. We see that the grams, the units of grams of NaCl cancel, and we're left with moles of NaCl, which is what we want. In the calculator, you do 737 divided by 58.44. And the calculator answer is 12.611, etc. So we want to run this properly. And looking at the given amount, we have 3 sig figs. The molar mass has 4 sig figs in the grams. The 1 mole is exact. So you keep 3 sig figs. And so you keep the 1, the 2, and 0.6. What comes after the 6 is a 1. So you keep the 6 as it is and drop everything after. And so the answer is 12.6 moles of NaCl. So we'll add another conversion to this because we will need to sometimes go all the way to molecules or particles. So when handling large numbers of molecules, it is impossible to measure by counting molecules. So instead, we count by mass, right? When you are in a lab, you're not able to count number of molecules or count number of moles. What you do is you take your substance and you're able to take the mass of it. So that's why we are dealing with masses, and then we need to retrieve the number of moles or of molecules by doing calculations. And so you can then use the molar mass to convert between grams and moles, and then the Avogadro's number to convert between moles and particles. So let's look at this in shape of a roadmap. So let's say you're in a lab, you know the grams of your substance, and you want to find out how many molecules you have. So from the grams, you can get the number of moles using the molar mass of your substance. Of course, you need to know the formula of your substance. And then when you have the moles, you can obtain the number of molecules using the Avogadro number. That's what we covered in the previous section, where we learned that we can use the definition of the mole to calculate between moles and number of particles. And so let's practice this. So how many copper atoms are in a penny weighing 3.10 grams? The given amount here is 3.10 grams. The question is asking for how many copper atoms. So it's asking for a number of atoms. Atoms, remember, are particles. So if we write the roadmap, we can see that we start with grams and end with atoms, but there is no direct relationship between grams and atoms, and we have to go through moles. And we know how to go from grams to moles and then from moles to atoms. So that's the way to go. So that means we will need 2 conversion factors. One that will relate grams to moles. And here we are dealing with copper atoms. So you want to find the molar mass of copper atoms. The molar mass is what relates grams to moles. So in the periodic table, find copper and find its molar mass. And copper is 63.55 grams per mole. So you can write it as an equality like this. 1 mole of copper is 63.55 grams of copper. And then the second conversion factor will change the moles into atoms. And for this, we've learned earlier that we need the definition of the mole, which says 1 mole of copper, and you adapt the unit and say 1 mole of copper is equal to 6.022 times 10 to the 23rd atoms. So the conversion factors from this, so the first conversion factor should take into account the given amount, the given unit, and the first conversion factor will want to cancel the given unit because the given unit is in grams. So you will want to use the molar mass of copper and have the grams in the denominator. So you will use the molar mass by having the 1 mole on top and the 63.55 grams on the bottom. This way you cancel grams from the given amount. Next, you want to multiply by the second conversion factor, and the second conversion factor should cancel the unit of mole, because that's not what we want ultimately. What we want is atoms, number of atoms. So the second conversion factors should have the mole on the bottom to cancel with the mole from the previous conversion factor, and the atoms on top, because the desired unit should finish in the numerator in the last conversion factor. So when we put this together and write the full calculation, so you always start with the given amount. So here it's 3.10 grams of copper times the first conversion factor, which is the molar mass, with the mole on top and the grams on the bottom. And we can see that it cancels the grams, times the second conversion factor with the mole on the bottom and the atoms on top. The moles on the bottom cancels with the moles from the previous conversion factor. And the atoms are the unit left, and that's the desired unit. So that's what we want. In your calculator, you type 3.10. Let's do all the numerators first. So times 6.022 second x minus 1 to get the capital E, and then type the exponent 23. So that's you know, the scientific notation in my calculator. So adapt to your calculator. And then you divide by the only denominator here, and it's dividing by 63.55 equals. And so the calculator answer is automatically in scientific notation, because there is no way to show a big number like that. And it's 2.93756, etc. times 10 to the 22nd power. So you want to pay attention to sig figs. You know, the 1 moles are exact. The Avogadro number has 4 sig figs. The grams from the molar mass have 4 sig figs. And the given amount has 3 sig figs, because the 3.10 here has 3 sig figs due to the fact that we see the decimal point. So the 0 is significant. So we want to round to 3 sig figs, so we will keep the 2.93. What comes after the 3 is a 7, so you want to round up the 3 to a 4, and then drop everything after that. And don't forget to record times 10 to the 22nd. If you forget to record that, this is a wrong answer, okay? It's a very, very large number, you know, close to the Avogadro number, because when we are dealing with a number of particles, those numbers must be very large and very similar to the Avogadro number. And here it's atoms of copper for the unit. Let's practice some more with this question. What is the mass of 4.78 times 10 to the 24th NO2 molecules? So again, I want you to practice this on your own before you watch the answer, because that's the only way to learn. So What is the given amount? Here it's 4.78 times 10 to the 24th NO2 molecules. What is the question asking for? It is asking for the mass, and so it's going to be in grams of NO2, because mass is in units of grams. Writing the roadmap, you will start with NO2 molecules, which are particles, and then you will end with grams. But there is no direct relationship between molecules and grams, so you will need to go through moles. So the roadmap looks like this: moles of NO2, then you need to convert that to, molecules of NO2, convert that to moles of NO2, and then convert again to grams of NO2. So we will need two conversion factors. The conversion factors, let's write the first one, between moles and grams of NO2. When you have a calculation to change grams to moles or moles to grams, you should automatically think molar mass. And here we will need the molar mass of NO2. So you pick up your periodic table, look at the molar mass of N and the molar mass of O times 2, and you add them all together, and the molar mass of NO2 should be 46.01 gram. So written as an equality, it's 1 mole of NO2 equals 46.01 gram. And then the other conversion factors should change the molecules to moles. And this should ring the bell of the definition of the mole and the Avogadro number. And so you adapt particles here should be molecules of NO2 and mole of NO2. So the two conversion factors should look like this. So starting from molecules to go to moles, the conversion factors should have the molecules on the bottom and the mole on top. This way we cancel the starting unit of molecules. And notice here how molecules, you cannot write just MOL or MOLE from, as an abbreviation for molecules. You cannot do that because this is the abbreviation for mole. The abbreviation for mole is MOL, or you can write MOLE. But if you have molecules and you don't want to write the whole word, you have to go all the way to the C to show that it's molecules and not moles. So then the second conversion factor should change the moles to grams. And so we will cancel the moles, the units of moles. So we will want the second conversion factor to have the moles on the bottom and then the grams on top. So writing the whole calculation, starting with the given amount. So 4.78 times 10 to the 24th molecules of NO2 times the first conversion factor is such that the molecules, the Avogadro number of molecules is on the bottom. So molecules cancel. And the moles of NO2 are on top. The second conversion factor should have the moles on the bottom because we want to cancel moles from the previous conversion factor in the numerator. And the grams on top. So the units cancel properly and we end up with units of grams, which is what we want. In the calculator, you do 4.78, the second function of the x minus 1 key to get the capital E, 24, the exponent, times, let's do the numerators first. So times 46.01. And now let's do the denominators. So divided by 6.022. Please, this is very important here to get the EE key and not do times 10 power because the calculator will move the times 10 power to the numerator if you do that. So make sure you make the calculator understand it's one number together. So use the EE function and then type the exponent 23 equals. And if you've typed properly, the calculator answer is 365.2072, etc. The number of sig figs, there is 3 in the given amount, 4 in the Avogadro number, and 4 in the grams of the molar mass. The 1 moles are exact. And so the least number of sig figs is 3. So we keep 3. We keep the 3, the 6, the 5. And what comes after the 5 is the 2.2. It's smaller than 5. So you just drop everything and keep the 5. And here the decimal point is implied when you have a non-zero digit. So the answer is 365 grams of NO2.